lecture notes for Chapter 5 on work, and we'll start off with Section 1. Section 1 deals with work and the definition of work. What is work? To many people, the word work means something you do to earn money. The word work also means exerting a force with your muscles. Someone might say they have done work when they push as hard as they can against the wall that doesn't move. However, in science, the word work is used in a different way. And again, just like some of the other terms like weight and temperature and heat, we're talking about the scientific definition of work, which is different than like the layman's term for the definition of work. Remember that a force is a push or a pull. In order for work to be done, a force must make something move. Work, by the definition, is a transfer of energy that occurs when a force makes an object move. If you push against a desk and nothing moves, then you haven't done any work. There are two conditions that have to be satisfied for work to be done on an object. One is that the applied force must make the object move, and the other is that the movement must be in the same direction as the applied force. Again, two conditions. One is that the applied force must make the object move. So if you're pushing against the wall for work to be done, the wall has to move. And the other is that the movement must be in the same direction as the applied force. So if you're pushing against the wall has to move in the direction that you pushed it. An example, when you lift a stack of books, your arms apply a force upward and the books move upward. Because the force and distance are in the same direction, your arms have done work on the books. So, in this example, the girl is picking the books up off the floor. The force is in the same direction. She's moving the books. When you carry books while walking, you might think your arms are doing work. However, in this case, the force exerted by your arms does no work on the books. And in this example, she has the books at this level, even though she's walking in this direction. The books are still at the same level, so she's not doing any more work on the books. The force exerted by your arms on the books is upward, but the books are moving horizontally. The force you exert is at right angles to the direction the books are moving. Alright? Again, she has the books stationary here. She's moving in this direction, but she originally lifted the books in this direction. So when they're stationary, she's not doing any more work on the books. Work and energy. When work is done, a transfer of energy always occurs. This is easy to understand when you think about how you feel after carrying a heavy box up a flight of stairs. You transferred energy from your moving muscles to the box and increased its potential energy by increasing its height. You may recall that energy is the ability to cause change. Another way to think of energy is that energy is the ability to do work. If something has energy, it can transfer energy to another object by doing work on that object. When you do work on an object, you increase its energy. Student carrying the box transfers chemical energy in his muscles to the box. Energy is always transferred from the object that is doing the work to the object on which the work is done. In this example, the boy or man isn't doing any more work on the box. He lifted it up to this height, but he's not doing any more work because the box isn't moving. Even though he's moving with the box up these stairs, he's not doing any more work, scientifically speaking, to the box. Calculating work. The amount of work done depends on the amount of force exerted and the distance over which the force is applied. When a force is exerted and an object moves in the direction of the force, the amount of work done can be calculated as follows. Work in joules equals applied force in newtons times distance in meters, or work equals force times distance. This is one of the formulas you'll need to know for this chapter. In this equation, force is measured in newtons and distance is measured in meters. Work, like energy, is measured in joules. 1 joule is about the amount of work required to lift a baseball a vertical distance of 0.7 meters. Suppose you give a book a push and it slides across along a table for a distance of 1 meter before it comes to a stop. Even though the book moved 1 meter, you do work on the book only while your hand is in contact with it. Power. Suppose you and another student are pushing boxes of books up a ramp and load them into a truck. To make the job more fun, you make a game of it, racing to see who can push a box up the ramp faster. Power is the amount of work done in 1 second. It is a rate because it's measured over time, the rate at which work is done. So power is the rate at which work is done. To calculate power, divide the work done by the time that's required to do the work. So power, and here's a new SI unit. Power measured in watts equals work in joules divided by time in seconds. Power equals work divided by time. The SI unit for power is the watt, expressed as a capital W. And again, another good test question, the SI unit of power. And 1 watt equals 1 joule of work done in 1 second. Calculating power. Because the watt is a small unit, power often is expressed in kilowatts, a term that your parents are probably more familiar with. Kilowatts. Our electricity is measured in kilowatt hours, or how many kilowatts did we use per hour, and then that rate is calculated, and that's how you pay your electric bill. Kilowatt equals 1,000 watts. Power and energy. Just as power is the rate at which work is done, power is also the rate at which energy is transferred. When energy is transferred, the power involved can be calculated by dividing the energy transferred by the time needed for the transfer to occur. And like I said in class, this equation isn't seen, or you don't use it as much as, you don't see it as much as the standard equation for power, work divided by time. But power, because work is energy, a transfer of energy, you can express power in these terms. Power equals E over T, where E is the transfer of energy in joules divided by the time in seconds. This completes the read for section 1. I'll go through these questions, and your assignment will be posted to My Big Campus along with these lecture notes. And you can find the assignment, the review section, in your My Big Campus account. Question 1 asks, blank is a transfer of energy that occurs when a force makes an object move. Conversion, energization, power, or work. And the correct answer is work. In order for work to be done, the applied force must make the object move in the same direction as the applied force. Question 2. The amount of work done depends on what 2 things? The answer is the amount of work done depends on the amount of force exerted and the distance over which the force is applied. Question 3. Which of the following equations can be used to calculate power? Power equals work divided by time. So this question is out. Again, I said power equals work divided by time. So this question is out. And I can draw it for you. Power equals work. Oh, what happened here? Power equals work divided by time. So that, if you look at question number C, or letter C, time equals work divided by power, so question C is the correct answer. Or answer C is the correct answer. Power equals work divided by time. And like I said, this concludes the read for section 1 of chapter 5.